So now that you've spent all of this time remastering the quadratic formula, let's talk about the ways that you can avoid having to use it. So you've seen some examples where you might get lucky and have a perfect square in your solution, but we're going to talk about when that doesn't happen, and we're looking for ways to simplify the algebra. So it's something called the x is small approximation. And when we say x is small, take a second and remember where we put x in our race table. It goes in initially in that change row. So when we say that x is small, what we are looking for are cases where the amount of change in the reaction as it's trying to get to equilibrium is small enough to approximate. Obviously, we're going to set out some criteria for this. So if x is small enough to approximate, that means the reaction is already close to equilibrium. So this is something that you have all of the tools to work with at this point, because we'll have equilibrium constants for these. So if you look at where the reaction is, what the reaction wants to get to, you don't necessarily have to calculate a Q to get this. We can look at values and make some judgment calls. So a reaction already close to equilibrium means that if you have a small KEQ, then you have high concentrations or pressures of the reactants. If you have a large KEQ, then you have high concentrations or pressures of the products. Now, they have to be the word high is really qualitative. So in terms of magnitudes, for small KEQ, high concentrations of pressures and reactants, you want a difference of about 10 to the third. For a large KEQ and high concentrations or pressures of products, we're going to say that your KEQ should be at least on the order of 10 to the third. So we are going to do examples, so you will get to see this. So here is one case. So you set up your race table, and before you go to set up the equilibrium constant expression, take a look at it. Is your reaction already close to equilibrium? Do you have a really small KEQ with a lot of reactant already, meaning you only have to form a tiny bit of product to get to equilibrium? Do you have a large KEQ and already a lot of product, meaning you only have to form a little bit of reactant to get to equilibrium? Or are you stuck? So this approximation is going to be the only option we have for higher roots. So I don't know about all of you, but I cannot factor and solve anything with, say, x to the third, x to the fourth, x to the fifth, especially not with the calculators that we are allowed to use in this class. So this x is small approximation, assuming that we are also close to equilibrium, will be the only possibility for solving something that has a cubic root and higher. And, we've seen plenty of reactions that have coefficients of 3 and 4 and 5, or as you'll see in the example, the coefficients don't go that high, but you have a couple of products or a couple of reactants that really quickly give you higher powers of X. Now, this video will talk about all of the cases where it works, and when we make this approximation, there's a test at the end to see if it was a good approximation. The next video will talk about what you do when it's not a good approximation. So let's do an example of this. So we're going to look at the reaction 2H2S gas in equilibrium with 2H2 gas and S2 gas. So you can see already when I write my equilibrium constant expression, I'm going to have H2 squared times the S. So if I have an X in either of those spots, I'm going to end up with a cubic root. So the problem that we're going to do is, let me get this set up for my rice table. We have an initial concentration of H2S of 0.0250 molar, and the reaction has an equilibrium constant Kc 1.67 times 10 to the minus 7th at 800 degrees. And we need to find the product concentrations at equilibrium. Okay, so we can get this started in our rice table. So we have the reaction. I have an initial concentration here of 0.250. I don't have any products when I start out, so my reaction has to move to the right. I'm going to lose 2x of the H2S and make 2x of the H2 and x of the S2. So in my equilibrium row, 0.250 minus 2x, 2x, x. And if I were to set up my equilibrium constant expression, which let's just write the actual expression over here. So H2 squared times S2 over H2S squared. So when I plug the equilibrium row into this expression, so my 1.67 times 10 to the minus 7th equals 2x, that whole quantity squared, times x, which doesn't need parentheses, but sometimes it helps me just keep things clear, and 0.250 minus 2x, this quantity squared. So if I multiply all of this out, I absolutely have a cubic root, right? I'm going to have 4x cubed in the top, and then I have to expand the stuff in the bottom, so I'm going to have x squareds and x's. So I will have a full cubic root equation that I don't have the ability to solve at this point. So the x is small approximation, what we're saying is that my equilibrium constant is really small, right? It's times 10 to the minus 7th. If I compare it to my starting concentration, so 10 to the minus 7th from my KEQ, my reactant concentration. I'm going to put this, right, if I do a little, right, that'd be 2.5 times 10 to the minus 2. These are apart by 10 to the 5th. So that's more than 10 to the 3rd. So I can assume in this case, at least to start, we're going to test it at the end, that X is small. Meaning the amount of change in this row will be very, very tiny. Now, it will still be something, right? We've talked about how you have to have some kind of concentration of product or reactant to be at equilibrium. But if X is really tiny, then 0.0250 minus 2X should basically be 0.0250, or really, really close to it. So close to it that based on sig figs, which we're not really dealing with this semester, it's almost exactly the same number. So when we say that X is small, we're going to go in here and eliminate that minus 2X. So my equilibrium constant expression with all of the numbers plugged in, the simplified form is going to be 1.67 times 10 to the minus 7th equals 2X squared times X divided by 0.0250 squared. So I still have an X cubed in here, but I only have an X cubed. So once I simplify all of this algebraically, I'm just going to need to take a cubed root in order to find my value of X. So I've completely eliminated the need to do quadratic formula, and hopefully I'll end up with something that's pretty close to the right answer, and we're going to test that at the end. So X is small means eliminate this subtraction of X, or it might be a plus X, and if you have it in multiple terms, you would eliminate it from multiple terms. So you will get everything down to where it's really straightforward to solve for X algebraically when you get to it. So if we do this, we end up with 4X cubed is equal to 1.67 times 10 to the minus 7th times 0.0250 times 0.250, and then we'll multiply out, divide by 4, take a cubed root, and X comes out to be 2.97 times 10 to the minus 4th. So we did get a really small number. So first of all, that's a good thing. We have to test this to see if it was a good assumption. So was it a good assumption? The way to test this is to see if is X very small compared to the number it was being added to or subtracted from. And by very small, we mean less than or equal to 5%. So very small means less than or equal to 5%. So the way to calculate this is the value for X divided by, I know it's a long line, it's going to look really silly, the number X was subtracted from or added to times 100 to give you a percentage. So we calculated 2.97 times 10 to the minus 4 for our x value. X was subtracted from 0.0250. If we do that division and multiply by 100, we get 1.19%. This is great. It means that our assumption was good, and we can use this approximation. So our x value that we can carry forward to solve the rest of the problem is 2.97 times 10 to the minus 4th. Now, we're still not done solving the problem, right? We were asked to find the product concentrations at equilibrium. So all this tells us is that we can now use x equals 2.97 times 10 to the minus 4th to find the product concentrations. Okay, so the product concentrations, H2, in our rice table was equal to 2x. So H2 concentration is 5.94 times 10 to the minus 4th molar, and the S2 concentration was just equal to x, so 2.97 times 10 to the minus 4th molar. And once again, if you would like to check your answer, you can take these numbers and plug them back into the equilibrium constant expression. Now, you might not get the exact number for the equilibrium constant value, but we made an approximation. It should still be very close.